This video explores the topic of Rogowski coils within the framework of the European project titled Personalized Education in Measurement, Science and Technology, Empowered by Machine Learning. Rogowski coil, which is a type of current transducer, is a coreless or air-cored coil that operates according to Ampere's law. It measures alternating or transient currents by sensing the magnetic field induced around a current-carrying conductor without requiring a magnetic core, thereby eliminating saturation and hysteresis effects common in ferromagnetic core transducers. Consider a conductor of length L, shaped into an elliptic loop enclosing a surface area S. If a separate conductor carrying a current IS with a current density J passes through this surface, the relationship between current, magnetic field, and magnetic flux density can be derived from Maxwell-Ampere's law as indicated. Therefore, the knowledge of magnetic flux B along L allows us to determine the current I that generated it. In practical applications, the Rogowski coil is a long, uniformly wound toroidal coil of length L with N turns surrounding a current-carrying conductor with current I. In this case, given the resistance and inductance of the winding current, and the mutual inductance between the current-carrying conductor and the winding, it is possible to derive the following relationship between the instantaneous voltage induced in the coil, Vc, and I, according to Faraday's law of electromagnetic induction. When the voltage Vc induced in the Rogowski coil is measured using an instrument with a sufficiently high input impedance, the loading effect on the coil can be neglected. Under this assumption, the current through the coil winding is minimal, and the induced voltage is governed primarily by Faraday's law of electromagnetic induction as described. To obtain the instantaneous current IT from the measured voltage VCT, the output must be integrated. This integration can be implemented using either analog integration, using an operational amplifier configured as an integrator, or digital integration, where VCT is digitized and numerically integrated in real time using digital signal processing techniques. Like all electromagnetic transducers, the Rogowski coil is subject to environmental influences, particularly temperature variations, which can affect its accuracy and stability. These effects mainly arise from two mechanisms: variation in the coil geometry and variation in the electrical resistance of the winding due to temperature variations. If the measuring system is designed such that RL is significantly higher than RC and it remains stable across the operating temperature range, the thermal variation in RC introduces only a small fractional error that can be compensated using the voltage divider effect. This can ensure a passive thermal compensation to provide a high and thermally stable load resistance. Moreover, Rogowski coils can be affected by crosstalk from magnetic fields perpendicular to the coil section. This effect can be mitigated by using a compensating winding or by constructing the coil with an even number of layers. Additionally, Rogowski coils introduce errors due to the discretization of the coil integral, which arises from the finite wire thickness and non-ideal winding pitch. Further errors can also result from imperfect centering of the current-carrying conductor inside the coil. Rogowski coils are lightweight, non-intrusive, and do not require direct electrical contact with the conductor. They also offer a wide measurement bandwidth and avoid core saturation, making them suitable for measuring high, rapidly changing currents. They are also manufactured in two typical coil designs: a rigid toroidal coil and a flexible loop version. Both types share the same underlying principle, but the flexible coil is easier to install around conductors of different sizes and in crowded environments. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement, Science and Technology, Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.